Distinguish between functions and relations. A relation, it's a set of ordered pairs. Now the first set of components of each ordered pair is called the domain, and other names could be input value or independent variable. And the second component of each ordered pair is called a range, and other names there are output values or dependent variables. So what you see in front of you is a set of 5 ordered pairs. So if I want to go ahead and look at the domain values, that'd be 1, 2, 3, 4, and 5. And if I want to turn around and look at the output values, well, that would be 2, 4, 6, 8, and 10. And what I want to do is to determine if this relation that is in front of us truly is a function. And to be a function, what has to happen is each of the input, every one of the inputs has to be sent to exactly one output. So if I go ahead and just list, just so I can visually see my input values, they would be what? What would be my input values?
There would be 1, 2, 3, 4, and 5.
And 5. And then I want to turn around and list each of those output values. What would they be? That would be
2, 4, 6, 8,
and 10. So one way of visually thinking about this is to take each input value and send it to the corresponding output value. In other words, if I look at the coordinate pair of 1, 2, I'm saying 1 is sent to 2. So I turn to you and say, for the next input value, what is it sent to? It's sent to
4.
So 2 is sent to 4, and then
3 is sent to 6.
3 is sent to 6.
4 is sent to 8.
4 is sent to 8.
And 5 is sent to 10.
5 is sent to 10. And where my eye goes is to each of the input values. Are they sent to 1, not 2, not 3, but 1 output value? And if they are, then this relation is a function. If they're not, the relation is not a function. So a function is a relation in which each input value is assigned exactly one output value. Now the input values, they're called what? They're called the
domain.
Output values are called
the range.
The range. And we say the output is a function of the input, like y is a function of x. So this particular set we have in front of us, well, this set does, in fact, represent a function. This relation is a function. So I'm going to take a look at now 2 more sets of coordinate pairs and ask a very basic question, which is which set represents a function and which set is a relation that's not a function. And if I want to be visual about this whole thing, what I'll do is go ahead and take a look at my inputs for my very first set. Well, my inputs are what? My inputs are...
Your inputs are 1, 2, 3, 4, and 5.
Okay. And my outputs are what? My outputs are...
Odd and even.
Odd and even. Some of them kind of repeat, so the unique ones are the...
Odd and even.
The odd and even values, if you will. So I'm going to go ahead and now assign each input to its corresponding output by looking at each ordered pair. So 1 corresponds to...
To odd.
Okay. 2 corresponds to...
To even.
3 corresponds to...
To odd.
Odd. 4 corresponds to...
Even.
Even. And 5 corresponds to...
Odd.
5 corresponds to odd. Good. So you're asking yourself, when you look at this set right here, right there, are each of these values, or each of these input values, going to 1 output?
They are.
They are. So that means that this relation is a function. So I would just say yes, yes it is. I have my outputs repeating, but I don't care about that. What I don't want is the inputs to repeat. Let's go to the next set and do the exact same thing. Let's list the input values. So you would tell me to list what? You would tell me to list
Odd and even.
I'm going to write down odd, and I'm going to write down even. Now I'm going to list the output values. Sorry, I said that horribly. You're going to tell me what the output values are so I may list them. What are they?
1, 2, 3, 4, and 5.
Very good. So now I'm going to go to each input and say, what is the corresponding output? So go to the first input, which is?
odd.
And it's sent where? It's sent to
It's sent to 1,
1,
3,
3.
and 5.
Uh-oh. Why uh-oh?
It isn't a function.
It's not a function. This relation is not a function because this input is sent to how many outputs?
3,
How many are they allowed at most?
1.
Brings us back to uh-oh, right? So here the answer would be no, 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 no. This is a relation that is not a function. Now, this is something that we're checking when we're giving coordinate pairs, right? What happens if we want to check the exact same concept when we're given the formula for a function? We can still answer the same question. So the question still holds. Determine whether the relation represents y as a function of x. So what I'm going to do is go to my very first relation, and I'm going to, strangely enough, pick a value of the input so I can actually see it. I'll pick 1 and see how many outputs it's sent to. And how do we do that? We're going to solve for y. So if I solve for y here, the first step would be to do what? It would be to
Divide both sides by 4.
So now I have 1/4 is equal to y squared.
Right.
Then what will I do?
Take the square root of either side.
And the square root of 1/4 is plus and minus 1/2. So I have plus and minus 1/2 is equal to y.
Right.
Now the interpretation is so very important. The interpretation goes just like this. This input of 1 is sent to how many outputs?
2 outputs.
2 outputs. So what does that mean? Does that mean that this relation is or is not a function?
It is not.
And that would be because why? Because that one input is sent to
2 outputs.
2 outputs, and it can only be sent to
It can only be sent to 1, so it's 1 too many.
1 too many. I like that. That's very good. So we're going to go ahead and say, no, this relation is not a function. I'm going to go ahead and take a look at my second relation, y equals 4x squared, and do the exact same thing. I'm going to pick a value for what? I pick a value for the input. I pick a value for x. And the value I'll pick is 1. So I got y is equal to 4 times 1 squared. And what's 4 times 1 squared?
4.
4. And again, it's the interpretation that matters. For this input value of 1, how many outputs is it sent to?
1.
1. So in this particular case, does this violate the definition of a function?
No.
No. So we'd go ahead and say, since it doesn't violate the definition of a function, that this relation, well, this relation truly is a function. Thank you. Which table or tables shown below represent a function, if any? Now, when we're given a table of input and output values, we want to check to see if each of the input values is paired with only one output value. If so, this table of input and outputs represent a function. And if not, well, the table does not represent a function. So let's look at the first table. What do we see? Well, we see that f of 2 is equal to 1. F of 5 is equal to 3. And f of 8 is equal to 6. Now our I goes here first. And notice we have 3 unique inputs, and each input corresponds to only one output. So our I goes here second. So this first table represents a function. So the answer would be yes. Take a look at the second table. What do we see? Well, we see that f of negative 3 is equal to 5. We see f of 0 is equal to 1. And f of 4 is equal to 5. Again, our I goes here first, and we have 3 unique inputs. And notice each of the inputs corresponds to only one output, so our I goes here second. This second table does represent a function. Notice our outputs can repeat. That's okay. What we want to avoid is a table where the inputs repeat. Take a look at the third table. What do we have? We have f of 1 is equal to 0, while f of 5 is equal to 2, and f of 5 is also equal to 4. Our I goes here first. And we notice that 5 is paired with 2 different outputs. This violates the definition of a function. So this third table does not represent a function. Our inputs, in particular the 5, are not set up so that they're paired with one output. 5 is paired with 2 outputs, violating the definition of a function. Functions and relations. Evaluate functions at given values. Hello. Today we're going to evaluate a function at an input. And what this means is you're going to find a corresponding output for the given input. Now remember, when you evaluate a function, this will always produce exactly one result. Why? Each input corresponds to exactly one output. So what we have before us is a function. F of x is equal to 5 minus 3x squared. And if I want to evaluate it for an input, and I'm going to pick an input to evaluate it for. So let's go ahead and pick, how about 10? If I evaluate this function at 10, what this means is that I'm going to substitute a 10 in for x, and we'll see what the output would be. So if I wrote this out, we would have 5 minus 3 times 10 squared. So the first thing we would do is square the input value. That would be what? That would be
100.
100. We're just following the order of operations here. Next thing we'll do is we'll multiply by 3. That gives us what? That gives us
300.
300. So now we have 5 minus 300. And then we'll do the subtraction. And the subtraction would give us what? It would give us
Negative 295.
very good. So what we've done, just to make sure we're very clear about this, is for the input of 10, we evaluated the function, and we found the output to be negative 295. So if we wrote this as an ordered pair, it would be what? It would be what, comma, what?
10, comma, negative 295.
Very good. It would be 10, comma, negative 295. Let's evaluate the same function, 5 minus 3x squared. And notice with our notation, we're going to evaluate at what? We're going to evaluate at
A plus h.
a plus h. So we're going to substitute a plus h in for the variable x. Now when we do that, we would have f of a plus h is equal to, which tells us this is what our output is equal to. And we have 5 minus 3 times, and then in parentheses, to make sure we're seeing what we're doing, we're going to place a plus h, or substitute in a plus h for x. And then we're just simply going to square that. So let's go ahead and just perform the order of operations. First thing we do, just like we did before, is we're going to square the term.
Right.
When we square the term, maybe we'll go off to the side here and do that. We'll have a plus h squared, so that's a plus h times a plus h. And if we multiply it through, well, the outside terms would give us what? It would give us
A squared.
a squared. If I multiply the inside terms and combine them, what would I get?
You would get a times h plus a times h.
And how many of those terms would it be?
2.
2a plus h.
Right.
And how about if I multiply the very last terms?
H squared.
H squared. Very good. So I'm going to replace a plus h squared with a squared plus 2ah plus h squared. And I'm just evaluating, that's all I'm doing. So I'm going to go ahead and now write this is equal to, see if I can grab the right color here. This is equal to 5 minus 3 times, and I have a squared plus 2ah plus h squared. So now let's distribute the negative 3. That would be next for order of operations.
Right.
And if I do that, I would have 5.
Minus 3a squared.
Good. And how about distributing the negative 3 to the next two terms?
Minus 6ah
Very good.
minus 3h squared.
Excellent. Now at this point you just want to check to see if you can simplify further, which in this particular case you can't, and to make sure that you are seeing what we've done. For the input a plus h, we have the output 5 minus 3a squared minus 6ah minus 3h squared. That output is the output that corresponds to a plus h in this function. And if I can do this type of an evaluation off of a formula, I should be able to do it off of a table. And if I do this off of the table, all you have to remember, is that when you evaluate the function, and here we're going to evaluate the function at 1, and then we'll evaluate at 4. The 1 and the 4 are the inputs. They're the inputs. And we're just asking for what the corresponding outputs would be. So if I go ahead and take a look at f of 1, that input of 1 corresponds to an output of
17.
17. And how about the input of 4? If I evaluate f of 4, that would be
23.
23. And so I can go ahead and write f of 1 as 17, but that just means that if I was looking at an ordered pair, the input is 1, the output is 17.
Right.
Here the input is what? The input is
4.
4, the output is
23.
23. Well, if I can now read the outputs off of a table, if I can evaluate a function from a table, I should be able to evaluate a function from a graph. So where I look at this problem and pause, I say to myself, I want to evaluate a function at 4 different inputs, -1, 0, 4, and 3. So I find -1, 0, 4, and 3, and I decide what would be the corresponding outputs. So let's go ahead and take a look at the very first input, which is -1. If I look on the graph, gosh, I have a point right there. And the coordinates of that point would be what? It would be?
-1 and 4.
And 4. So now it makes it easy. If I want to find what is f of -1, the corresponding output would be
4.
4, which is my y coordinate or my f of x coordinate. If I take a look at my second evaluation, I'm evaluating f of 0. So I take a look at where x is 0, and that would then be along the y-axis, and I would read off the point. What would that point be?
That would be 0, 1.
Very good. So if I evaluate f of 0, I'm asking for the output when the input is 0, and that output would be
1.
1. Well, we have 2 more of these to do. There would need to evaluate the function at 4. So I go ahead and take a look at the function itself and realize, gosh, my graph doesn't extend upward till 4. So if it did, I would pick a point up there, and I would evaluate that particular point. All right. How about f of 3? That I can grab, though. What would f of 3 look like? Well, if I go ahead and find the point right here, let's see if we can find the point when the input is 3, what would the coordinates of that point be?
It would be 3 and 4.
Okay, so the input would be what? The input would be?
3,
Output would be?
4.
4. So if I ask you to evaluate the function at 3, you would say the output that corresponds to it would be?
4.
4.
4. Beautiful. Thank you very much. We're going to evaluate this difference quotient using this function, f of x is equal to x squared plus 3x minus 4. So the first task is to find f of a plus h. The next task is to find f of a, and then we'll subtract in the numerator and simplify. Let's get going. F of a plus h is found by substituting in a plus h for x in our function. So this would give us a plus h squared plus 3 times a plus h minus 4. And now we're just going to simplify. We'll multiply through the terms. This gives us a squared, ah plus ah is 2ah plus h squared. I'll distribute the 3. This would give us 3a plus 3h minus 4. I look for terms to combine. I don't see any. Now I'll evaluate f of a by substituting in for x, a. Well, this gives us a squared plus 3a minus 4. Here I have no terms to combine. And I'm ready to start the problem. I'm going to go ahead and substitute in f of a plus h. So I need your eye to look at this difference quotient and realize that I'm substituting in f of a plus h, which is a squared plus 2ah plus h squared plus 3a plus 3h minus 4. Then I'll subtract away f of a, and f of a is a squared plus 3a minus 4. And I'm going to divide by h. Now at this point, all I really want to do is simplify. So my first task is to distribute this -1. It's like adding a -1 is subtracting. So I'll multiply that through to 3 terms, and I'll have -a squared minus 3a, and then minus a -4. Well, that would be plus 4. And I'll cross out what I just changed. Now I look to simplify, and I realize I can. I can cancel a squareds. What else can I cancel? The 3a's, and a -4 and a plus 4 adds to 0. Notice what we have left. What we have left is 2ah plus h squared plus 3h all over h. And the very last step is to factor out an h from the numerator. So if I factor out an h from the numerator, I'm left with 2a plus h plus 3, and in the denominator I have an h. To finish simplifying, all I'll do is cancel the h's. And when I evaluate this difference quotient, what I get is 2a plus h plus 3. We'll evaluate the function at h of 4. And the function we have is h of p is equal to p squared plus 2p. Now our input variable is p. So h of 4 means that p is equal to 4. So we want to go ahead and replace the p with a 4 in each location that we see the p. So our notation is very important. We start by writing h of 4 is equal to, and we're looking for the output. And according to our function, it's p squared, which is 4 squared, plus 2 times p, 2 times 4. Now we just evaluate. We have h of 4 is equal to 16 plus 8, which is 24. So we've evaluated the function at h of 4. h of 4 is equal to 24. 24 is the output for the input of 4. Solve for inputs of functions from given outputs. Recall, if you have an ordered pair, x, f of x, the input is the x and the output is the f of x. So what we're going to do is we're going to solve for inputs of functions from given outputs. What this means is that if you're solving, we know an output value and we want to determine the input value that gives that output value. So we'll give you a formula for a function, and what you'll do is you'll set that output value equal to the formula and you'll just solve for x. And bear in mind, you can end up in a case where you can have several solutions because an output could correspond to several inputs with a function. Now we're going to look at 3 examples in a row, and we'll look at 3 common algebraic techniques. In our first case, f of x is defined to be, let me just switch colors here, f of x is 10 minus 3x. And we want to solve f of x equals -1. So what we're going to do is we're going to say to ourselves, we're looking for the input so that that output is -1. So it's really just a substitution. I'm going to replace f of x with 10 minus 3x, and then that is set equal to -1. Now I just solve. So to solve, that's where you jump into the picture. If I want to solve, if I want to isolate the x, the first step would be to...
You subtract the 10?
Okay, let's subtract the 10 from both sides of the equation.
Sure.
So I have -1 minus 10, which is...
-11.
Very good. And really just one more step, I'll...
Divide the -3.
Very good. I'll divide both sides by -3. So I have -11 divided by -3, and that reduces to...
11 over 3?
11 over 3. Now the nice thing is we can check the answers here. And to check the answers, all I'll do is evaluate the function at that input. I'll evaluate the function at the input, and the input was what? The input was...
Was -1.
The input was... Because the -1 was the output, the input was...
11 over 3.
11 over 3, and I want to see if that output is...
-1.
-1. So I'll substitute in for 10 minus 3x. I'll substitute in for the x, 11 over 3. And what do you see? If you're doing the order of operations, the first thing you would do is...
Right, you would subtract. You would multiply the 3.
Okay, and 3 divided by 3 would be?
Would be. Oh, you can cancel those.
You can cancel those.
10 minus 11.
Be 10 minus 11. What is 10 minus 11?
-1.
And what should the output be?
It needs to be -1.
Fantastic. 1 down, 2 to go with a different algebraic technique. For the second one, all we're going to do is set the output equal to 15, and we're going to take the function's formula. And here the function is what? The function f of x is equal to x squared minus 2x. So here I'm looking for the particular input whose output is 15. So I'm just going to make a quick substitution. I'll go ahead and replace f of x with the function's formula. And the function's formula is...
X squared minus 2x.
Very good. So I have x squared minus 2x equal to the output I'm given, which is?
15.
I'm trying to figure out the input that would give me that output. So I want to solve, and I do have a second degree equation. So I want to go ahead and set the equation to 0. What am I driving at? What's my first step?
So you would subtract 15.
Okay, let's subtract 15 from both sides of the equation. And to solve this, I'll go ahead and
Factor?
And I'll multiply in my mind 2 numbers that would multiply to...
To negative 15.
Okay, so I'll multiply 2 numbers that would multiply by something, and then you get negative 15, and then they would have to add to be what? They would have to add to be...
To be negative 2.
Have to add to be negative 2. All right, so what would those factors be? So set up my factors, set them equal to 0. The first terms will be?
Would it be... Well, the first terms would be x.
X, and then the numbers to multiply to give you negative 15, yet add to give you negative 2.
Minus 5.
Very good.
And then plus 3.
Beautiful. Once we do this, we double check. Negative 5 times 3 is?
Is negative 15.
Negative 15. Negative 5x plus 3x is?
Negative 2.
All right, now we go ahead and just set each factor equal to 0, and we solve. So x minus 5 is equal to 0, or x plus 3 is equal to 0. And if we solve, the 2 solutions would be x is equal to?
5.
Or
negative 3.
Or x is equal to negative 3. And how many inputs give us that output value of 15?
1.
1. Let's see, how many inputs here give us that output value of 15? 2. Very, very good. And that's possible. You can go ahead and have an output with more than one input. What you cannot have is an input with more than one output. We're good, in other words. We're good. Is this checkable? Can we check this if we wanted to?
Yes,
Yes.
we can.
Let's check it. Let's check it quickly, though. Let's evaluate the function first at 5. And so if I substitute into the formula, 5 squared is?
25.
And then I'll subtract away 2 times 5, which is?
Which is 10.
10, and that output that I would get would be?
15.
15, and that's what I'd like. And if I go ahead and check by evaluating the function at negative 3, I get negative 3 squared, which is?
9.
Negative 2 times negative 3, which is?
18.
Negative 2 times negative 3, which is 18? Is that
Oh,
right?
sorry. Negative
Yep. Negative.
6.
Yep. So
Positive 6.
Okay, so and which one of those 3 do you like the best?
6.
Okay, we'll put the 6 down. And then 9 plus 6 is?
15.
15. Does this check? Do we get the outputs of 15?
Yes.
Yes, we do. Okay, one more. We want to find the input, so the output is 2. The function we're given is f of x is equal to the square root of x plus 6. So I'll go ahead and do what? I'll go ahead and set my formula equal to?
2.
2, and I want the input, so the output is 2.
Right.
So what will I do? I want to get rid of this square root. What will I do to both sides of the equation? I will
You will square both sides.
square both sides of the equation. Does that look like I'm squaring both sides of the equation?
It does
Yes.
to me.
Square root of x plus square root of this x plus 6, and we're squaring it. We end up getting back,
X plus 6.
and 2 squared is
4.
4. And then if I subtract 6 from both sides of the equation, I get?
Negative 2.
Negative 2. And a lot of students will go ahead and say, gosh, I can't get a negative response back because I have a square root in the actual function itself. But that's not true at all, is it? You don't want that square root, it's a principal root, to be equal to a negative. But the input could be equal to a negative 2. Now, if you say, well, you don't have to go through that. Why don't you just check it? My response is, let's go ahead and just check it. Takes just a moment to check. If I evaluate the function at
negative 2.
I should get back
Positive 2.
positive 2. So if I go ahead and set this f of negative 2 equal to the square root of negative 2 plus 6,
Right.
I end up with f of negative 2 to be equal to the square root of,
4.
4.
and that's the principal root, isn't it? That's the principal root of 4.
Yes, it is.
And the principal root of 4 is?
Is 2.
Is 2. Thank you. We want to solve for p if h of p equals 3 for the given function. The function we're given is h of p is equal to p squared plus 2p. Now, be mindful that p is an input, and h of p, well, that's an output. So when we see that h of p is equal to 3, that means the output is 3. And the output is given by p squared plus 2p. So we substitute p squared plus 2p for h of p, and this gives us p squared plus 2p is equal to 3. Now we want to solve for p. Well, because we have a quadratic equation, we'll go ahead and set it to 0. I'll subtract a 3 from both sides of the equation. This gives us p squared plus 2p minus 3 equals 0. The best case scenario is that this particular quadratic equation factors, and it does. We set up our two factors to be equal to 0. We need numbers to multiply to negative 3, but add up to plus 2. So that would be a plus 3 and a minus 1. And in the front would be a p and a p. So our factors are p plus 3 times p minus 1. Next, we set each factor equal to 0 and solve. So we write p plus 3 is equal to 0. Or the other solution is p minus 1 is equal to 0. Let's look at p plus 3 is equal to 0. I'll subtract a 3 from both sides of the equation. This gives me p is equal to negative 3. That's one of the inputs that would have an output of positive 3. For p minus 1 is equal to 0, I'll add a 1 to both sides of the equation. This gives us p equals 1. That is the other input for an output of 3. So what are the two values of p, where h of p is equal to 3? Those two values are p is negative 3 or p is 1. Find values of functions graphically. What we're going to do is read off a graph to find either inputs if given an output or outputs if given an input. When we use the term evaluating a function, what we want to do is think that we're given a value of x and we're looking for the output. So that means we're looking for the second coordinate in our pair of coordinates. And so we want to find the corresponding output from that input. And if we're solving a function equation, but we're using a graph, then just the opposite is true. We're given the output with an ordered pair. That would be the second coordinate. And we're looking for the input, the first coordinate. So evaluating, we're given x, we're looking for f of x. Evaluating, given x, looking for f of x. Solving, just the opposite. Given f of x, looking for x. Given f of x, looking for x. So for any point on our graph, just to make sure we're saying the same thing, so I can highlight it here. There we go. Then we were writing the point as x f of x, and the input is the first coordinate, f of x is the second coordinate. So let's evaluate f of 2. If I evaluate f of 2, the first thing I'm going to do is write down f of 2 is equal to, and we're looking to evaluate, so we're given a input or output?
Input.
Input, and we're looking for the
Output.
output. So the input here is what? The input here is
2.
2. And so if I go ahead and take a look at the ordered pair at 2, it would be 2 comma
0.
0. So the output when x is 2 would be?
0.
Very good. So f of 2 is 0. Let's do this again. That would be A. For B, let's evaluate f of 3. Well, we're given an input or an output.
We're given an input.
And the input is?
Is 3.
Is 3. So let's find that particular point on the graph and let's write down the coordinates. And the coordinates would be 3,
1.
3, 1. So we're given the input, we want the output.
Right.
The output when the input of 3 is given would be?
You get 1.
You get back 1. In the very last case, we look to solve. So that means we're given an
Output.
and we're looking for a
Input.
input. So if I'm given f of x is equal to 4, my output is 4. So now I have to say, well, gosh, my output is 4 in how many locations?
2.
2. Very good. So if I go ahead and write down the coordinate pairs, what would the coordinate pairs be when that output is 4?
It
Here's 1 point.
would be 0, 4.
0, 4.
And the other one would be 4, 4.
4, 4. Very good. Now here I do want to be very clear. I'm given an output. That's what you told me. So I'm given an output of 4. And I'm looking for an input. I'm looking for the corresponding inputs would be what? Which would be
0.
0 or
4.
or 4. So x equals 0 or x equals 4 would be the solution. Thank you. Given the graph of f below, we want to evaluate f of 2 and we want to solve f of x equals 4. So before we begin, the very first thing we want to do is remind ourselves that points on a graph are given by x, f of x. So along the horizontal axis, which I see right here, I have the inputs, and along the vertical axis, which I see right here, I have my outputs. So with this in mind, the first thing I'm going to do is I'm going to say to myself, let's start with f of 2. f of 2 looks like we're looking for an output. And we're looking for an output when the input equals 2. So I go to the inputs, find where x equals 2, project up to the graph, and I see that I have coordinates of 2, 1. So this means that when I evaluate f of 2, the output at 2 is that y coordinate, which is 1. Now in the second case, what we're going to do is we're going to solve when f of x equals 4. So if I go ahead and write f of x equals 4, it looks to me like I'm given an output, and I'm looking to find the input. Don't know what it is. So let's find the outputs along the vertical axis, and we're going to look for the output y equals 4. Easiest way to do that is just to draw a horizontal line at y equals 4. That will give me the outputs. And I notice that I have 2 points whose y coordinates are 4. One point is negative 1, 4, and the other point is 3, 4. So again, I'm looking for the x values when y is 4. The two x values are negative 1 and also 3. And just to make sure you and I are saying the same thing, when I evaluate the function at negative 1, what do I get back? I get back a 4. And when I evaluate the function at 3, what do I get back? I get back a 4. Graphs of functions and relations. Apply the vertical line test. Hello. Remember, a function is a relation in which each possible input value is assigned one output value. Now, we can represent a function using a graph. And when you do this, what we do is we sketch a horizontal axis, we call that the x-axis, a vertical axis, call that the y-axis, and then when we sketch the actual function itself, the points on the function are written x comma y. So the first coordinate is the input, the second coordinate is the
output.
The output, good. And the question we have is, if we have a graph of a relation, how do we know if that relation is a function? And the answer is that we apply the vertical line test, because the vertical line test will tell us very quickly if the graph of the relation is a function. and it says that if you draw vertical lines, if any vertical line hits this graph in more than one location, well, that relation is not a function. Take a look at the very first graph we see. We see a single vertical line, but imagine any vertical line you can sketch. Every vertical line would intersect that function in how many locations?
Just one.
Just one, and that's why I say it's a function. Look at the second graph. We see a single vertical line. Even the one we see intersects the graph of this relation in how many locations?
2.
2. So this relation is not a function. Why? Because for our input value that we're seeing, and this input value here would be 3, well, it would correspond to 2 different outputs, and that violates the definition of a function. So, your turn. Use a vertical line test to determine if the graph of the relation you see is really a function. Look at the graph on the left. Ask yourself, will any vertical line hit the graph in exactly one spot, or will there be a vertical line that would hit it in 2 or more spots? So, graph on the left.
Yes.
Is this a function?
No,
I don't believe so.
No. Why?
because the vertical line would hit the graph in 2 spots.
In 2 spots. In fact, I can draw many vertical lines that would do that. Is that right?
Yes, you can.
And for any of these inputs, and here's an input that I'll highlight in red, then that input is associated with how many outputs?
2.
2, and that violates the definition of a function.
Right.
So this particular graph is not a function. Take a look at the second graph. For the second graph itself, would this graph represent the graph of a function?
I think it would.
Yeah.
Because any vertical line that you could conceivably draw would intersect the graph in
Just one location.
one location. So each input would be assigned
One output.
one output and no more. So to determine if this graph is a function, we imagine these vertical lines being sketched, each vertical line hitting the graph in one spot. We do have the graph of a function. Thank you. Which of the graphs shown below represents a function? Now what we're going to do is apply the vertical line test, which states that if any vertical line intersects the graph more than once, well, the graph does not represent the graph of a function. So look at the graph on A. No matter how we sketch the vertical lines, each vertical line will hit the graph only once. So that means for X, which is the input, it will correspond to only one Y, which is the output. So this particular graph is the graph of a function. Look at the second graph. As we sketch vertical lines, again, notice no matter where we sketch the vertical lines, it would intersect the graph only once. So each input is assigned only one output. This is the graph of a function. Now for our third graph, if I go ahead and sketch vertical lines, notice that I do have vertical lines that intersect the graph more than once. So for any input, I'm looking at 2 outputs that would correspond. This would violate the definition of a function, so the graph of this particular circle is not going to represent the graph of a function. Determine if functions are one-to-one, algebraically or graphically. Well, we know for a function that each input has to have one output. A one-to-one function says each output in turn has to have one input that corresponds to it. And what this does is it creates a one-to-one correspondence between the inputs and the outputs. So the way we say this is every element of the range corresponds to exactly one element of the domain. Now, to determine if a function is one-to-one, we will do this first algebraically, and what we'll do is we'll set 2 outputs equal, and that means that when I go ahead and find the corresponding inputs, I best get one input as a result. So let's determine if this function is a one-to-one function. Now, the way I get 2 outputs is, since my function is 3x plus 2, I'll get one output from letting the input be A, so I'll have 3A plus 2, and the other output from letting the input be something different, like B. And what I want to do is set these equal and see if I find if A is equal to B. And if it is, if A is equal to B, I do have a one-to-one function. So what I'm going to do is subtract a 2 from both sides of the equation. This gives me 3A equals 3B. And notice if I divide both sides of the equation by 3, A equals B. Those inputs are equal. So what we do have is a one-to-one function. When I go to the second example, I'll do the exact same procedure. And notice the two equations look rather similar, don't they? But watch what happens when we look at the results. I'll grab two inputs, A and B, and I'll assign their outputs to be equal. So what would their outputs look like? It would be what? It would be
3A squared plus 2
very good. And that would be set equal to
3B squared plus 2.
excellent. So much as I did before, my first step would be to
Subtract 2.
from both sides of the equation. And this gives me what? It gives me 3A squared equals 2.
3B squared.
Very good. And my next step would be to what?
You would take the square root of either side.
You
I
could.
believe.
What could we do before that, though?
Maybe divide the 3.
Maybe divide by 3. And this gives me what? It gives me A squared equals
B squared.
B squared. Now come back to that thought you had. What are you going to do to both sides of the equation?
I think you would take the square root of either side.
You would. If you take the square root of either side, you find that A could be equal to B, or A could be equal to what?
To negative B.
Negative B. And what you want to do is interpret this. So you have a single output, but you could be assigning it two inputs.
Right.
So this violates our definition of a one-to-one function. This function is one-to-one. No, it's not a one-to-one function. Now, if I can look at this algebraically, I should be able to look at it graphically. And if I want to look at it graphically, I'll use something called a horizontal line test. So the way a horizontal line test is going to work is that I'll draw horizontal lines through the graph. So imagine, if you will, a graph of a function. So here is the x-axis and here is the y-axis, and then I'll draw a function here in blue. And then my horizontal lines, I'm going to imagine drawing horizontal lines. And the thing is, if any horizontal line intersects the graph in more than one spot, and here we're intersecting the graph in 1, 2, 3 spots, then this output, whatever y equals c is, whatever that c value is not assigned one input. In this case, it's assigned 3 of them. That's a lot of words there. What do you need to remember? Well, if any horizontal line hits the graph or intersects the graph in more than one location, then your function's not one-to-one. Let's see if you got it. You know how we can see if you got it? We give you 4 quick problems to do. We want to determine if the function whose graph is shown is a one-to-one function. As I proceed to draw horizontal lines through the graph of this function, each horizontal line does what?
It intersects the graph once.
Once. So what does that mean as far as this question is concerned? Do we have a one-to-one function?
Yes.
Okay, so the way it's worded, determine if we have a one-to-one function. In the first case, we do. Let's go to the second case. Let's go ahead and start sketching horizontal lines. There's a bunch of them. And so the majority of these horizontal lines intersect the graph in
2 locations.
2 locations. So that means for that output, you're assigning it how many inputs?
More than 1.
More than 1, and that's what's key. So this function is
Not one-to-one.
not one-to-one. I bet you can tell what's going to happen. If I take a look at the third case, I'll go ahead and say, gosh, let's see if I can make that look just a little better here. What'd you say? Not what? Not
one-to-one.
Not one-to-one. There you go. Now it stands out. All right, how about the third case? Let's go ahead and take a look at sketching, if we will, horizontal lines. It seems like all these horizontal lines, what's the end of that sentence?
Intersect the graph once.
Once. So our conclusion is that
It is one-to-one.
That function is a one-to-one function. In the very last case, if I start sketching my horizontal lines, I notice that for the most part, these horizontal lines intersect the graph in,
Two
spots.
locations.
yep, more than one, two locations, and that means my conclusion is that the function is
Not one-to-one.
not one-to-one. Very good. Excellent. Thank you. The amount of garbage G produced by a city with a population of P is given by G is equal to the function of F evaluated at P. Now, G is measured in tons per week and P is measured in thousands of people. The town of Tola has a population of 10,000 and produces 8 tons of garbage each week. Express this information as a function F. Well, we know that for part A, G is equal to F of P. Our input is P, and this is our population of the town, and it's measured in terms of thousands of people. The output, G, this is the amount of tons of garbage the town produces. So when the population is 10,000, P would be the number 10, because 10 times 1,000 is 10,000. And again, the population is measured in terms of thousands. This town produces 8 tons of garbage, and G again is measured in terms of tons. So we have F of 10 is equal to 8 as the function representation of this scenario. B, explain the meaning of the statement F of 6 equals 3. So for B, if we have F of 6 is equal to 3, again, 6 is our input. It's the population in thousands. So 6 times 1,000 is 6,000. So this 6 represents 6,000 people in the town. Now the output that we see, 3, refers back to tons of garbage. This is the number of tons of garbage they've produced. So if I was going to interpret the meaning of this statement, I would say a town of 6,000 people produces 3 tons of garbage. And I have my interpretation. So when you see F of 10 equals 8, you're thinking a town with a population of 10,000 will produce 8 tons of garbage. And when you see F of 6 equals 3, you will think to yourself a town of 6,000 people will produce 3 tons of garbage. Evaluate functions at variable amounts. Now we've looked at evaluating a function, but we're going to evaluate a function when the input is a variable. So just a couple of pieces of information that we already know. Given an input value, we want to determine a corresponding output value. And when you do this, you will always produce one result because each input is assigned or corresponds to one output. So what you're basically going to do is substitute in the input and you'll run it through the function's formula to get the output, and in doing so we will follow the order of operations. So if I gave you f of x is equal to 5 plus 3x squared and I substitute in a value for x, I would go ahead and square. I'd multiply by 3, I'd add 5, I'd follow the order of operations. So let's go ahead and see if we can, there we go, evaluate the function f of x is equal to 5 plus 3x squared. And we want to evaluate it at negative a, which means that I'm going to make a substitution, rather you're going to make a substitution right off the bat. You'll substitute negative a for x. So as far as notation is concerned, we write down f of negative a is equal to 5 plus 3, and then we substitute in for x, we substitute in a
negative a,
and we square. Input's negative a, the output is what we get when we simplify. Well, we go through order of operations. Negative a squared is...
Is positive a.
No, sir.
It is
A squared.
A squared, very good. So now we have 5 plus 3a squared. And I really can't go any further, and there is my corresponding output when the input is negative a. Let's go ahead and take a look at two more. Here, we want to evaluate the function at a and then apply the negative. So we're going to evaluate negative f of a. So it's the order that we're doing this that we want to be mindful of. Our first substitution, just to be really clear, is we're going to substitute in for x, what?
A.
A. So that means I'm going to write down negative f of a, and I'll take negative, and then I'll go ahead and do that substitution. And when I do that substitution, notice I'm taking negative of two terms. I have 5 plus 3 times
a squared.
A squared. Very good. And so now when I write down negative f of a, again, just to be as clear as I can possibly be here, this negative will go right here.
Right.
So we end up with negative, and I'll distribute the negative, rather you'll distribute the negative through the two terms, and you end up with?
With negative 5.
Very good.
Minus 3a squared.
Very good. And there is negative f of a. Let's do one more valuation where we go ahead and take a look at an expression. And the expression is f of a plus h minus f of a over h. And we're going to have to evaluate this function at the variable input, or the variable itself a, and also a variable input of a plus h. We're going to have to subtract the two and divide by h. Now, there was a lot of words there, but it goes something like this. Let's find f of a plus h first.
Sure.
Oh, we can do that. We'll go ahead and write down f of a plus h. And I'll substitute in for x, what?
A plus h.
A plus h. I'm going to write that down. So I have 5 plus 3 times, instead of x, we have
A plus h.
Squared.
squared. Very good. Now I do want to simplify this a little bit. So off to the side, I'm going to think through, if I have, I can grab a nice color here, a plus h, and if I'm squaring it, I'm multiplying it to itself, times a plus h. Multiply the first terms, I get
A squared.
a squared. The two middle terms combined, that ah and ah, would combine to be
2ah.
very good. And then the last terms would give me what?
H squared.
H squared. So I'm going to replace what I'm underlining here with a squared plus 2ah. So we're just simplifying this first term is all we're doing. It's taking a moment, but that's what we're doing. We're going to write 5 plus, and I'm going to go ahead and multiply 3 by a squared plus 2ah plus h squared. But I really didn't do well verbalizing that sentence. I'm not going to multiply through by 3. You are. So we end up with 5 plus what? 5 plus?
Plus 3a squared.
Good. Plus?
Plus 6ah.
Very good.
Plus 3h squared.
Super. Do you see any terms you can combine at this point, or are we done for the moment?
It's looking about done.
Looking about done. So what we've done, just to be very, very clear, is we just evaluate f of a plus h.
Right.
So now we want to evaluate f of a. This should be a little bit quicker, I would think, if I want to evaluate f of a. I'm going to write f of a is equal to, and now I'm going to substitute in for x and a. This will be a little bit quicker. What would that give me? This would give me
5 plus 3a squared.
very good. Good news, we can start the problem now. We can go ahead and say, let's evaluate f of a plus h minus f of a over h. So I'll write f of a plus h minus f of a all over h, and this would be equal to f of a plus h, which is 5 plus 3a squared plus 6ah plus 3h squared. That's what we have here. minus f of a.
Isn't it plus 3h squared?
Very good. Good catch. 3h squared. Thank you. And then I'll subtract, so I'll put the subtraction sign in. And I'll subtract f of a, and f of a is what? F of a is?
F of a was 5 plus 3a squared.
Very good. And I'm dividing by what? Dividing by?
Dividing by h. And I don't think the square held over the 3h yet.
Oh, did I write it and it didn't stay?
There we go.
There we go. Thank you so much. I wrote it and it didn't stay. So now we're going to distribute the negative out front. So when we distribute the negative out front, we end up with 5 plus 3a squared plus 6ah plus 3h squared. And then when I distribute the negative out front, I end up with what? I end up with?
Minus 5 minus 3a squared.
Super. All over what? All over?
All over h.
H. Well, do you notice any simplification that we can do?
Absolutely.
What would that be?
The 5s cancel out.
5 minus 5 is 0. That sounds good.
And there's a 3a squared and a negative 3a squared.
That sounds good. Anything else?
You should be able to take out the h.
Let's do that.
Divide that through.
Let's factor out the h. So if I factor out the h, I think to myself, how many terms are now left over in the numerator?
There's 2.
2. If I factor out an h, what would that leave?
A 6a plus 3h.
Very good. And when I divide by h, you notice that you can do what? You can
Cancel out the h's.
cancel out the h's. So we finally get to what f of a plus h minus f of a over h is, which would be what? Which would be
6a plus 3h.
super. Thank you. Use technology to graph given functions or relations. We're going to use technology to graph a function, and the function that we're going to graph each time is f of x is equal to x squared with 3 different viewing windows. So the purpose of this video is to show you how to actually do that, how to find a domain and range to fit the domain that's given. So in the very first domain interval we have, we're going to graph it on negative 0.1 to 0.1. So what you'll do is you'll go into your graphing calculator, and where you actually have y1, you'll enter the function x squared, x raised to the second power. What you need to do then is set a viewing window so that the domain is from negative 0.1 to 0.1. So to do this, you'll go into Window, and for x minimum, you'll pick the left side of the interval, so that's negative 0.1, and for x maximum, you'll pick the right side of the interval, and that's 0.1. So I went from negative 0.1 to 0.1. Now I then have to find the corresponding range values so I can see the graph. All I've done is enter the horizontal extent. To do that, some calculators have a zoom fit feature, zoom fit, and all you would do is hit zoom and then fit. Other calculators you may need to set manually. To set manually, this is the thought process. What you want to do is set y minimum, so I'll write y minimum, and think about the smallest y value that can be taken on in this interval. Well, if the function is y equals x squared, whenever you square a number, it's always what? It's always square a number, it's always
Squared.
Positive.
positive. Very good. So it's always what or more? It's always
0 or more.
All right, so y minimum would be 0. For y maximum, I do have an image of this shape in my mind, and I say to myself, gosh, let me go ahead and try the right side or the left side of this particular interval by evaluating the function at negative 0.1 and positive 0.1. And when I do this, I get 0.01 in each case. So that's what I'm going to let y maximum be. And when I do that, I see this graph right here. So let's go ahead and change the viewing window to make sure we're okay with different domain intervals of finding the corresponding range. So, same function, but now I want to graph this function on negative 10 to 10. So I'll go into y equals, I'll enter y equals x squared.
Right.
So y equals x raised to the second. And then I turn to you and say I got to go turn to the viewing window.
Right.
And for x minimum, I will enter,
-10.
let me write that down. For x maximum, I will enter,
+10.
very good. Now for y minimum, what will I enter?
Y minimum, you put in 10 into the equation, so would you put in 100?
I think about the smallest output you can take on when the function is y equals x squared. What would be that smallest output?
It's always positive, so it's 0.
0, very good. All right, and for y maximum, I think that's maybe what you were referring to a moment ago.
Right, yeah, that would be 100.
That would be 100 because I would evaluate the function at -10, at 10, just searching a little bit. But in each case, I do get back 100.
Right.
And so my y min would be 0, y max would be 100. Let's do one more. Let's do one more. Let's go ahead and look at f of x is equal to x squared. We're just going to look at from -100 to 100 for this particular interval. Same set of questions. First thing I do is I enter the function. The function is
X squared?
X squared.
okay, so I enter that function. Then I turn to the viewing window itself, and I want to enter what? X min and X max. So for this interval, X min would be
-100.
very good. See if I can write -100 so it's a little more legible. There we go. And for X max, I'll enter what? I'll enter
+100.
+100. Very good. So now that I've entered the domain, I want to find the corresponding range. So I have y equals x squared, f of x equals x squared. The smallest output would be
0.
0, so that means my y minimum would be what? My y minimum would be
It would be 0.
0, and for y maximum, what would my y maximum be?
You would square -100,
All right, let
and you
me,
would also square +100.
that sounds great. So let me write both down. And when I square those values, I end up with
10,000.
10,000. Very good. In each case. So my y maximum would be what? It would be
10,000.
10,000. Thank you. Solve applications involving functions. Teddy Bear Anonymous, or TBA, has an annual sales of teddy bears S by year T. And it's modeled by the function S is equal to f of T. Now, S is measured in thousands of teddy bears that are sold, and T is measured in the number of years since 2000. We're going to look at part A and B. And what part A will do, we'll take a sentence and ask us to write the sentence in function notation, while part B will just reverse the situation. Given the function notation, let's come up with a sentence. So the first thing I'm going to do is just write down S is equal to f of T, because that's what we're told. Now my input variable is what? My input is
T.
T, and I got to write this down. I think to myself, T represents what?
Years since 2000.
Very good. Very, very good. Years since 2000. Now the output is
S,
S. And S is really going to be what? It's going to be
the number of teddy bear sales in thousands.
very good. Number of teddy bear sales. I'm going to write TB for teddy bear. Number of teddy bear sales. What was the last phrase you said? In what? In
thousands.
very, very good. In thousands. All right, let's look at part A. And to do that, let me go ahead and just switch colors here. Okay. Teddy Bear Anonymous sold how many teddy bears? Looks like they sold 10,000 teddy bears in 2015. We want to express this information in terms of the function f. So we have S is equal to f of T. And our input is what? Our input for part A
Is T.
okay, T. And T represents the number of years since
2000.
2000. So what is the actual value of T?
Would it be 15?
T is 15. Very, very good. And then the output is what? The output is
10,000.
very good, 10,000. But the
It
actual
is.
way it's measured in
It's measured in thousands. So
in
would
thousands.
It be
Very
10?
good. Very good. So the value of S is actually 10. So if I write S, S is equal to
10.
10. Beautiful. Right, 10. And that's equal to f of what? F of
F of 15.
f of 15. Very good. Now we're going to go ahead and reverse the situation. Looking at something in function notation, we'll just explain what it means. All right, so again, I'm going to go ahead and pause and just change colors here. I want to explain the meaning of the statement f of 16 is equal to 11.5. So I'm just going to write that down. I'm going to write down 11.5 is equal to f of 16. What is my input value here?
16.
16, very good. And what does 16 actually represent?
That represents the year since 2000.
Okay, so what year would that be?
2016.
All right, so it looks like we're in 2016. What is the output value?
11.5.
Okay, and what does that represent?
The teddy bear sales in thousands, so would it be 11,500 teddy bear sales?
That's absolutely perfect. 11,500 teddy bear sales. Now all you have to do is phrase this as a sentence. Because I have f of 16 is equal to 11.5, that means?
In 2016, there was 11,500 teddy bear sales.
Beautiful job. Thank you. Toolkit functions. Identify and graph constant functions f of x equals b. Toolkit functions are a set of basic functions that we have where we need to know the graph, the formula, and the special properties. Some of these can be actually programmed on your calculator. They have keys for them. And in all of these functions, x is the independent variable, and y equals f of x is the output. So what we're going to do is we're going to look at these toolkit functions. We're going to see combinations of them and their graphs and their transformations throughout the entire course. And it'll be very helpful if we can recognize these functions by name. So what we're going to do is start with the constant function, f of x equals b, for b being any real number. What do we need to know about the constant function? Well, first we need to know what the graph looks like. So I'm going to go ahead and just plot really just 3 points. I'll have my inputs x, and my output says f of x. So I'll pick 3 different inputs. How about -2, 0, and 2? And in each case, what would the output be?
I think the output would be 3.
Would be 3, because we have the constant function, which just means for any input, the output is 3. So I'll plot -2, 3. I'll plot 0, 3. I'll plot 2, 3. And I'll draw the graph, and what we see is a horizontal line. And this is the graph of f of x is equal to 3. Well, now that we have a visual of the graph, let's see if we can read off of the graph the domain and the range. Now for the domain, this is the set of allowable inputs. My eye looks left to right. And I take a look at the graph that's in front of me, f of x is equal to b, and it looks like my domain would be what? It would be?
Would it be all real numbers?
All real numbers, because the graph extends for the left and for the right forever.
Right.
And that's why it's all real numbers. So my domain would be -infinity to infinity. That would cover all real numbers. And we always use open parentheses when we have intervals involving either infinity or -infinity. Well, next I want to find the range. For the range, my eye goes vertically. It goes from the bottom up. But here, when I take a look at the range, if I look from the bottom up, it's kind of a quick glance, isn't it? In other words, what are all the outputs?
Aren't they just 3?
Aren't they just 3? Sounds just good to me. They are. They're 3, or in this case, b, because we were thinking about that previous function, weren't we, when we said 3?
Oh, right.
So in this case, the range would be y is equal to what? Y would equal
B?
b, and b represents
The range.
the range, which
output.
could be any
Number.
real number. Very, very good. Very last thing we got to do is decide, is the graph increasing? So when I look from left to right, the graph goes up. Decreasing, when I look from left to right, the graph goes down. Or constant, is the graph horizontal? This particular function over the entire domain is one of these 3. And which one is it?
It looks constant.
It's constant, isn't it? Why is it constant? Well, it's a horizontal line that we're seeing. So because this function is constant over the entire domain, then I would say it's constant over the interval of, and what was the domain of the constant function?
Negative infinity to positive infinity.
Beautiful. And so we say this function is constant over the interval negative infinity to positive infinity. Thank you. Toolkit functions. We will identify and graph the identity function f of x equals x. Now, with our toolkit functions, we have some basic functions that we need to learn to recognize the graph, the formula, and some special properties. So we're going to look at the identity function f of x equals x. And we need to be able to recognize its graph, know its domain and its range, and finally be able to decide on what intervals is the function increasing, decreasing, or constant. So first things first, let's go ahead and plot the graph. And we'll just do this by plotting points. So I'm going to set up a table here. Remember, f of x equals x. So I'm going to pick three inputs. I'm going to pick -2, 0, and 2. And then I'm going to go ahead and write down the corresponding outputs. Now, if f of x is equal to x, if the outputs equal the inputs, when the input is -2, the output is?
-2.
-2. I'm going to write that in. When the input is 0, the output is?
0.
0.
And when the input is 2, the output is?
2.
2. So we'll plot those points. -2, 2, 0, 0, and finally 2, 2. And they fall along this line that I'm going to sketch. There is the graph that we need to be able to recognize for f of x equals x. Now next, we're going to identify the domain and the range. So if I go ahead and talk first about the domain is the set of acceptable inputs. We have to train our eyes to look left to right to decide the domain. Now notice this graph extends all the way to the left and all the way to the right. So the domain is all real numbers from -infinity to infinity. And we always use parentheses to go ahead and write this interval. Now for the range, we have to train our eyes to look vertically. This graph extends down forever and up forever. So for our range, again, it's all real numbers, -infinity to infinity. Now the last thing we have to do is decide if the function is increasing, decreasing, or constant, and what intervals that would apply. So we say to ourselves, okay, on intervals where the function is increasing, when the inputs increase, the outputs would increase. And so the graph would go up. For intervals that are decreasing, as the input increases, the outputs would
Decrease.
and the graph would go down. For constant intervals, as the input increases, the outputs would
Stay
Stay
the
the
same.
same.
stay the same, and the graph wouldn't go up, it wouldn't go down, it would be
Horizontal.
horizontal. Very good. So look at this graph. As you look from left to right, it seems like the graph is
Increasing?
increasing. So I'm going to go ahead and just write that in. My graph is increasing over the whole domain. And what was the domain of this function?
It was -infinity to infinity.
Beautiful job. Thank you. We're going to identify and graph the absolute value function. F of x is equal to the absolute value of x. Now, f of x equals the absolute value of x is one of our toolkit functions. So we're going to have to become familiar with it. We're going to have to know its formula, its name. We're going to have to know its graph and some special properties. We're going to have to know what the graph looks like, what the domain and the range is, and where the graph is increasing, decreasing, or constant as it pertains here. So the first thing we're going to do is take a look at the graph, and we're going to do this by plotting points. So I'm going to set up a table of points. I'm going to have the inputs as x and the outputs as f of x. And I'm going to choose three inputs, -2, 0, and 2. And if the outputs are the absolute values of those numbers, let's go input by input. The absolute value of -2 is 2, and the absolute value of 0 is
0.
and the absolute value of 2 is
2.
So we're now going to plot these. We plot -2, 2. We plot 0, 0. And we plot 2, 2. and we draw the function. And as we draw the function, we notice it looks basically like a V shape, doesn't it?
Mm-hmm.
And so this is the graph's shape that we have to become familiar with. Well, now I want to be able to recognize the domain and the range. And for the domain, I want to look horizontally from left to right. And for the range, I want to look vertically from bottom to top. So we'll start with the domain. The domain, it seems like it extends from the left to the right forever. So my domain would be all real numbers, negative infinity to infinity. And whenever you write these intervals where the negative infinity or the infinity is, you use parentheses. Next, we're going to look vertically because we're going to identify the range. Notice the lowest the graph appears seems to be right on the x-axis, and then the graph goes up forever. So as far as the range is concerned, writing these intervals from smallest to largest, what would be the smallest that range value would be? What's the lower end of this interval?
Would it be
0?
0?
0. And how would I write this interval if I want to include the 0? With a bracket or a parentheses?
A bracket?
With a bracket. Very good. And then it will extend up forever. The numbers get larger and larger. What am I driving at? The rest of the interval would look like what? It would be 0 to?
Infinity.
Infinity. And with the infinity symbol, we always use a
parenthesis.
parenthesis. Last, we're going to look at intervals where the function is increasing, decreasing, or constant. So with increasing intervals, as the inputs increase, the outputs?
They also increase.
They also increase, so the graph goes?
Up.
Good. For decreasing intervals, as the inputs increase, the outputs?
Decrease.
And so the graph goes?
Down.
Okay. For constant intervals, as the inputs increase, the outputs?
Stay the same.
Stay the same, so the graph is?
It's level. It's horizontal.
Horizontal. This particular graph seems to go down and then up.
It does.
So let's go ahead and take a look at where the graph goes down. That seems like it's from negative infinity all the way to?
0?
0. So my graph is decreasing from negative infinity to 0. And these intervals are always in terms of the inputs, x values, and we're always going to use parentheses to write them. Now notice, when I'm to the right of 0, the graph seems to go upward. So where this graph is going upward, we have an increasing interval, and that interval would be what? It would be?
0 to infinity.
Very good, because it's all values of x, all values of the input that are greater than 0. Thank you. Toolkit functions. Identify and graph the square function, f of x equals x squared. Toolkit functions. F of x equals x squared is one of our toolkit functions. We have to be able to recognize its graph and its formula and some special properties. We have to be able to see the graph in our mind's eye. We have to be able to recognize its domain and range and know where the function is increasing, decreasing, or constant. So first things first, let's go ahead and take a look at the graph itself. To do this, we're just going to plot points. So we're going to come over here and set up a table. I'm going to choose this part of the slide to write my table on. I'm going to have x and f of x. And for the inputs x, I'm going to choose three values, -2, 0, and 2. And for f of x, we're going to square each of those numbers. So when the input is -2, the output would be -2 squared, or
4.
4. When the input is 0, the output would be
0.
because you have 0 squared, which is 0. And when the input is 2, the output would be
4.
because that's 2 squared. Very good. Plotting these points, we have -2, 4, 0, 0, and 2, 4, and we have a graph whose name is a parabola. We have the graph, and we have the graph of a parabola. So the next piece of information we need is what is the domain and range of this function. And with domain, we have to train our eyes to look left to right. With range, we have to train our eyes to look down and then up. So let's start with the domain. Notice this graph extends from the left to the right forever. So the domain is -infinity to infinity. And with intervals involving -infinity or infinity, we always use parentheses to write as the ends of those intervals. Now, for the range, we again are looking down to up in that order. So the lowest the graph seems to be is right along the x-axis, and then it extends up forever. So our range, written smallest to largest, would go from
0
to,
infinity.
very good. Do we include the 0?
Yes.
Yes, that's because of that point 0, 0 that we looked at before, that output of 0, that second 0 in the ordered pair.
Right.
Do we use a bracket or a parenthesis when we include the 0?
Should be a bracket.
Should be a bracket, and with infinities, we always use a
Parentheses.
parenthesis. Lastly, we have to decide the intervals where the function is increasing, decreasing, or constant. Now, for increasing functions, where the inputs increase, the outputs,
Increase.
so the graph goes.
Up.
And for decreasing intervals, where the inputs increase, the outputs
Decrease.
Decrease.
decrease, and so the graph would go
Down.
down. And lastly, for constant intervals, when the inputs increase, the outputs,
Stay
the
the
same.
same.
and their graph would look like a
Horizontal line.
horizontal line. So this particular graph seems like it does what? Seems like it drops until you get to 0.
Right.
So that particular interval is what? It's
Negative infinity to 0.
very good. Negative infinity to 0. And with increasing, decreasing, and constant intervals, we always use parentheses. To the right of 0, notice the graph is going upward, which means what? Which means this function is increasing. Where? It's increasing.
From 0 to infinity.
Very good. Thank you. Toolkit functions. We need to identify and graph the cube function, f of x equals x cubed. Now the toolkit functions are a set of basic functions, and today we're looking at f of x equals x cubed. We need to be able to recognize the formula and the graph and some special properties. We need to be able to see the graph in our mind's eye and recognize and be able to read off the domain range for this function, as well as where the intervals are increasing or decreasing or constant. So first things first, let's see if we can get the graph up. We'll do this by plotting points. We'll go ahead and create a set of 3 inputs, -2, 0, and 2, and then find the corresponding outputs. Now remember, we have the cube function, so we're going to take each of these inputs and multiply them to themselves 3 times. So if the input is -2, the output would be
So
Negative 8.
-2 times -2 is 4 times -2 is -8. Good. How about if the input is 0, the output would be?
0.
And then if the input is 2, the output would be?
Positive 8.
Positive 8. 2 times 2 times 2. So now we'll graph these particular 3 ordered pairs, these 3 points. We have -2, 8. We have 0, 0. And lastly, we have 2, 8. And we have the graph of our f of x equals x cubed, our cube function. Well, once we have the graph in our mind, from the graph we need to be able to read off the domain. For the domain, we need to train our eye to look from left to right. For the range, well, we need to train our eye to look from bottom to top. So let's start with the domain. If I want to look at the domain, I look from left to right, and it seems the graph extends from left to right forever. So the domain would be -infinity to infinity. For the range, notice that this graph extends down to up forever as well. So my range similarly would be what? It would be?
Negative infinity to infinity.
Very good. Lastly, we have to decide the intervals for which this function is increasing, decreasing, or constant. So, where the function is increasing, as the inputs increase, the outputs
Increase.
in the graph goes
Up.
well. For decreasing intervals, where the inputs increase, the outputs,
Decrease.
and the graph goes.
Down.
And lastly, for constant intervals, where the inputs increase, the outputs,
Stay the same.
and the graph is
Horizontal.
horizontal. This particular graph seems like it's always what? It's always
Increasing.
increasing. And that's because when I look from left to right, the graph is going up. So if that's the case, where this graph is increasing would be everywhere on its domain. What was its domain? It was what? It was?
It's negative infinity to infinity.
Beautiful job. Thank you. Toolkit functions. Identify and graph the reciprocal function f of x equals 1 over x. We're going to look at the reciprocal function f of x equals 1 over x. This is one of our toolkit functions. You need to be able to recognize its formula, its graph, some special properties. You need to be able to see the graph in your mind. You need to be able to recognize the domain and range, as well as where the function is increasing, decreasing, or constant. So we're going to first start by plotting some points to see if we can visualize the graph. So I'll create a table of values, inputs x, outputs f of x, which again is equal to 1 over x. And I'm going to choose inputs of -2, -1, -0.5, 0, 1/2, 1, and 2. And you are going to give me the corresponding outputs. So again, if I have an input of -2, the function is f of x is 1 over x, that output would be?
It would be 1 over -2.
Very
or
good.
-1/2.
Or -1/2. How about if the input is -1?
It would be -1.
-1, because it's 1 divided by -1. Very good. How about if the input is -0.5?
I think it would be -2.
Very good, because basically you're taking the reciprocal, aren't you?
Right.
How about if the input is 0?
1 over 0.
1 over 0.
But can't you not do that because you can't have a 0 in the denominator?
Can't have a 0 in the denominator. So will we get an output there?
Would it just be undefined?
Just be undefined. Now how about if the input is 1/2, the output would be
2.
2. You're taking the reciprocal, you're
Right.
kind of flipping that particular fraction. When the input is 1, the output is
1.
and when the input is 2, the output is
1/2.
1/2. So now we'll go ahead and plot these points, and there's 6 points that we need to plot. So we'll take a look at -2, -0.5, be right about here, -1, -1, -0.5, -2, and I'm just going to continue to plot points in a moment, but let me draw that particular branch. As I get closer to 0 from the left, like -1/10, the output would be -10. And so this branch actually dips down as it approaches 0. When I'm to the right of 0, I'll plot my points. So I'll have 1/2, 2, 1, 1, and lastly 2, 1/2. And I'll go ahead and sketch that particular curve as well. And now I have a visual as to what this graph looks like. Once I have the graph in my mind, I'm going to determine the domain and range. And for the domain, I'm going to look from left to right in that order. And from the range, well, the range I'm going to look from bottom to top in that order. But remember, this graph is not defined at what x value, at x equals
0.
0. So let's start with the domain where we look from left to right. If I look from left to right, it looks like the graph is defined until I get to 0. And then it's defined again all the way to the right as far as that graph can go. So that means for the first interval that I see, and the interval that I'm talking about is right here, then when I write the domain would be what? It would be -∞ to 0. But I wouldn't include the 0, so I'll have parentheses by the 0 to show I'm not including it. And then I have to take a look at the second interval, which is right here. And I'm looking at all numbers that are now to the right of 0. So union just means or the second interval, and it would be 0 to infinity. And that would be all the inputs that are more than 0. For the range, we're going to go ahead and now look from bottom to top. So for the range, it looks like I'll go from -∞ up to what? Up to?
Up to 0.
0.
Up to 0. So let me write that in. And then what symbol did we use to join the intervals? We used
A big U.
big U for union. And then my outputs start to increase when I'm on the other side of the x-axis, so that interval would be what? It would be
0
to infinity.
0 to infinity. And again, I'm looking vertically at the extent of the graph. Now the last thing I want to do is take a look at where my function is increasing, decreasing, and constant. So for increasing intervals, when the input increases, the outputs
Increase.
and the graph goes.
Up.
And when I take a look at decreasing intervals, when the inputs increase, the outputs
Decrease.
and the graph goes.
Down.
And lastly, for the constant intervals, well, when the inputs increase, the outputs
Stay the same.
and the graph seems to be.
Horizontal.
Look at this graph. When I glance at it, I'm looking from left to right. So when I'm less than 0, this graph goes up, it goes down, it stays constant,
It
horizontal.
looks like it's going down.
It's going down. So that means the type of interval is what? It's going to be
Decreasing.
decreasing, and that's right here is what we're seeing is the graph going down.
Right.
So we're decreasing on negative infinity to what? To
0.
0. Now, are we defined at 0?
We're not.
No.
We're not, so I'll use a parenthesis to exclude 0.
Right.
Now I have a second branch to look at, and that second branch to look at is here. But as I look from left to right, the graph goes up or down or is horizontal.
Looks like it's still decreasing.
It's still decreasing. It's still going down. So I use a giant U for union. And what interval is it decreasing for that branch? For that branch that's to the right of 0.
0 to infinity?
Very good. Do I include the 0?
No.
No, so I use parentheses there as well. And so I'm decreasing on negative infinity to 0, union, or 0 to infinity. Thank you. Toolkit functions will identify and graph the square root function f of x equals the square root of x. F of x equals the square root of x is one of our toolkit functions. We're going to need to be familiar with its graph and formula, have a visual as to what the graph looks like, and be able to read off the domain and range and the intervals where the function is increasing, decreasing, or constant. So the first thing we're going to do is just plot points to get a sense of what the graph looks like. So I'm going to go ahead and choose some input values. So I'll go ahead and create a small table here. X for my input, f of x equals the square root of x for the output, and I'm going to choose the input of 0, 1, and 4, and the output would be, well, what's the square root of 0?
0.
And the square root of 1,
Is 1.
and the square root of 4,
2.
2. So let's plot these 3 points, 0, 0, 1, 1, and 4, 2. And I know x can never be, what? It can never be
Negative.
negative because inside the square root, which is called a radicand, that must be 0 or more. So I feel pretty comfortable that my graph looks just as I'm sketching right here. Well, the next thing to do is to read off the domain and range. For the domain, we want to look from left to right. And for the range, we want to look from bottom to top in that order. So for the domain, I'm seeing the graph start here and go to the right forever. So for the domain, it would start at
0.
And then if it's extending to the right forever, it would go ahead and have 0 to infinity as an interval. Would the 0 be included?
Yes.
It was.
So I would use a bracket or parentheses,
A bracket.
a bracket to include the 0. And infinities, they always get what symbol, a bracket or a parenthesis?
A parenthesis.
A parenthesis, good. So I have my domain. For my range, my eye shifts to go bottom to top. So the lowest the graph is right here, and then it goes up forever. So it looks like for the range, going from smallest to largest, the interval would be what? It would be
0 to infinity?
0 to infinity. Would we include the 0?
Yes.
Yes, so we would use a
Bracket.
bracket, and infinities always get a
Parenthesis.
parenthesis. Good. Lastly, we have to decide whether the intervals are increasing, decreasing, or constant. For increasing intervals, when the input increases, the outputs
Increase.
and the graph goes
Up.
And for decreasing intervals, when the inputs increase, the outputs
Decrease.
Decrease.
and the graph goes
Down.
And for constant intervals, when the inputs increase, the outputs
Stay the
Stay
same.
the same.
and the graph is.
Horizontal.
What's happening with this graph? It is always,
It looks like it's always increasing.
it's always increasing. When you look from left to right, the graph's going up. So we're going to go ahead and say our graph is increasing on its domain. What was its domain?
It was bracket 0 to infinity.
Perfect
with
job.
parentheses.
Perfect job. Thank you. Toolkit functions identify and graph the cube root function, f of x equals the cube root of x. F of x equals the cube root of x is one of our toolkit functions. We need to know its formula, its graph, and its special properties. We need to be able to recognize what the graph looks like. We need to be able to read off the domain and range and be able to know what intervals are increasing, decreasing, or constant. So the first thing we're going to do is just plot the cube root function by plotting points. So I'm going to go ahead and choose 5 different inputs, and that's what I'll go ahead and put on the left column, and on the right column I'll write the corresponding outputs. So I'll choose inputs of -8, -1, 0, 1, and 8. Well, the cube root of -8 is -2, because -2 times itself 3 times is -8. So the cube root of -1 is,
-1.
Negative
cube root of 0 is,
0,
cube root of 1 is,
1,
and the cube root of 8 is
2.
2. Now we'll plot these points. So I have -8, -2. I have -1, -1, 0, 0, 1, 1, and finally 8, 2.
I think you marked your -1, -1 at the wrong spot.
Well, you're absolutely right. Let me erase that. Good catch. So let's go ahead and make that change.
There we go.
Thank you very much. So I'll sketch my cube root of x, f of x equals the cube root of x function, and that's the visual that I need. Excellent catch. Now I need to be able to read off the domain and range, and for the domain I have to train my eye to look from left to right. For the range I have to train my eye to go from bottom to top, in that order. Now notice with this particular function, for the domain, it extends from the left to the right forever. So our domain would be what? It would be
-infinity to +infinity.
excellent. And on the ends of the intervals with the infinity or -infinity symbol, we always use parentheses. For the range, I have to train my eye to look from bottom to top. It looks like my graph will go ahead and go from down to up forever. So my range would be what? It would also be
-infinity to +infinity.
excellent job. Lastly, I need to be able to recognize where the intervals are increasing, decreasing, or constant. For increasing intervals, when the inputs increase, the outputs
Increase.
and the graph goes
Up.
And for decreasing intervals, where the inputs increase, the outputs
Decrease.
Decrease.
the graph goes
Down.
down. What am I going to say for constant intervals? When the inputs,
Increase.
Increase.
the outputs,
Stay the same.
and the graph is
Horizontal.
You don't even need me here. You know this, right? So notice this graph, when I look from left to right, is doing what? It is going,
It is increasing.
it is increasing. It's going up from left to right. So that means my graph is going to be increasing on its domain. And what was its domain?
-infinity to infinity.
Very good. Very well said. Thank you.